Greetings everyone. Welcome back. Welcome to another episode of the organic chemistry course. So on today's episode, we're touching on halogen derivatives. Our first subheading being halogenoalkanes. Halogenoalkanes, which we'll be dealing with, and halogen derivatives. Halogenoalkanes are classified into primary halogenoalkanes, secondary halogenoalkanes, and tertiary halogenoalkanes. If you watched the first video of the organic chemistry course, I also classified alcohols in the same manner, and I'm not going to be doing that here. But let me just try. Let me call this my other group, my carbon atom, my X here, my X for my halogen being chlorine, bromine, or iodine, right? So if the carbon atom, if the carbon to halide bond, if the carbon to halide bond, if this carbon to halide bond is attached to three other groups, is tertiary. Tertiary means three other groups, right? 1, 2, and 3. And if the carbon to halide bond is attached to two other groups, 2, it becomes secondary, right? And if it is attached to one other group, it's primary. Same. I hope you know that. So I'll be touching more on this in the next videos, okay? So I'm going to use a typical example using bromoethane as a typical example here. Bromoethane is my typical example. So bromoethane undergoes 4 types of reactions in which halogenoalkanes undergo, 3 of which are nucleophilic substitution reactions. So the first substitution reaction is the hydrolysis of our halogenoalkane. Bromoethane undergoes hydrolysis when heated in the presence of aqueous sodium hydroxide. This reaction is an example of a nucleophilic substitution reaction. The bromine atom here is replaced by an OH group, the OH coming from sodium hydroxide. The OH negative, the hydroxy ion, this one, is the nucleophile. Right, let's move on to the next subheading, formation of nitriles. Bromoethane also undergoes nucleophilic substitution when heated with sodium cyanide in alcohol, particularly, right? In this case, ethanol is just being used as a solvent. The bromine atom here is replaced by a cyanide ion, right? Which is my what? My cyanide ion is my nucleophile. Okay? This is my nucleophile. Right? Then of course, this also forms sodium bromide, just like the previous reaction. This reaction is a takeaway from this. This reaction is an important reaction in that it increases the number of carbon atoms in a chain. Say you have got an organic compound and you want to increase its number of carbon atoms. Why not try nucleophilic substitution of halogenoalkanes? Then you increase the number of carbon atoms in your chain. That's all. You're going to see how this applies in solving questions as we move on. Let's move on to the third example of primary amines, right? The subheading which is saying formation of primary amines. Primary amines are formed when halogenoalkanes are heated in the presence of concentrated ammonia in a sealed container. This reaction also takes place in an ethanol solvent, right? This also takes place in an ethanol solvent. Don't forget that, right? To produce a primary amine here and hydrogen bromide. This reaction is deserves most of our attention because more reactions will emanate from this one. Okay, let me say on this one as well, I'll try to do a separate video on this one, just this one, a very short video on this one alone, okay, to show you how this thing works. Now let's move on to the next subheading of this reaction, the mechanism, how this reaction takes place. The nucleophile in this reaction is in the third topic, the formation of amines, is NH3. NH3 is our nucleophile. The nucleophile attacks the bromoethane. Bromoethane, this is the structure of bromoethane that you see here. It has a polar C to Br bond. The C being partially positive, and so the bromine atom being, or the halogen atom being partially negative. So the positive, this nucleophile becomes attracted to the positively charged region, the partially positive carbon, leading to the formation of a pentavalent transition state. Right? Now, the NH3 to C bond is being formed while the C to Br bond is being broken, leading to the formation of a primary amine here and HBr, or hydrogen halide. This reaction is said to be an SN2 mechanism. I'm going to touch on this, okay? SN2 mechanism. I'm going to touch on this. Here, I'll just explain how it happens to say the nucleophilic ammonia attacks the partially positive carbon to which the electronegative bromine is attached, resulting in the formation of a pentavalent transition state. The C to Br bond is being broken as the C to N bond is being formed. The resulting organic product is a primary amine. Is here, it's ethylamine. The fourth reaction, remember I said bromoethane undergoes four type of reactions, right? 3 of which are nucleophilic substitution reactions. The fourth one is an elimination reaction, whereby we are trying to eliminate a hydrogen halide, right? So sodium hydroxide, the ethylamine, bromoethane undergoes an elimination reaction when it is heated with sodium hydroxide in ethanol, also known as ethanolic sodium hydroxide, to form an alkene plus a hydrogen halide. Now let us talk about that's what there is to it. Those are the only type of reactions, right? Now I'll move on to the next subheading there what we have here, nucleophilic monomolecular substitution, SN1, right? What is this one? This one is a type of reaction that takes place in tertiary halogenoalkanes. What's the tertiary halogenoalkane? It is an alkane whereby the C to halogen bond, the carbon attached to the bromine or the halogen bond is attached to three other groups there, right? To undergo, we're replacing the bromide, the bromine atom there, or halogen atom there, with an OH group of atoms there. So the reaction proceeds via two routes. The first one is the slow step, and this one is the second step. In the slow step, there is the formation of a carbocation. Right? Whereby the bromine atom there is ejected. Right? Then the carbocation then reacts with the hydroxyl ion to form a tertiary alcohol. Don't worry about that. Let's just say the OH group is replaced the bromine atom there. So here are the comments for this type of reaction. We are saying it is saying molecularity is 1. What do we mean? We are trying to say in the rate determining step, or the slow step of the reaction, we've got only one molecule existing. Only one, which is our tertiary halogen alkane. The reaction proceeds via the formation of a stable intermediate, which is the carbocation that we have here. The carbocation is stable because it is not reactive, right? So below, I drew the reaction profile, energy pathway diagram for the reaction, right? It looks somewhat like this because that's where we have got the stable intermediate here. It's a very stable intermediate. It's also called an activated complex. That's what I wrote here. It's an activated complex. I'm sure it's difficult to see properly. I know. Okay. Now let's move on to the next type of reaction. SN2 mechanism. From the moment we started this program, most of the three of the first three reactions bromoethane was undergoing were SN2 mechanisms. What were we saying? We're trying to say in the slow step of the reaction with two molecules, the bromoethane and the nucleophile. And all of them, they react in such a way that they form this pentavalent transition state, right? Transition state. Then from there, from the pentavalent transition state, we have the formation of our new molecule whereby the nucleophile is substituted the halogen plus the halogen anion that has been ejected here, bromide ion. So here, the same in the same way, the first three reactions, which are nucleophilic substitution reactions, proceed via the same mechanism. Okay, this is how the mechanism happens. I try to simplify everything there, right? So the molecularity is true. What are they trying to say? They're trying to say in the rate determining step or the slow step of the reaction, we've got two molecules occurring. That's what they're trying to say. And the graph or the energy profile for this reaction is the one similar. It's a normal one, like a normal exothermic energy profile that you've seen in your physical chemistry under chemical energetics, where there's the formation of an unstable intermediate, right? And then we form a product over there. Let's move on to the next subheading: reactions of halogenoalkanes and halogenoarenes, right? So we've got three molecules there, number 3, number 2, and number 1. Number 3 is an acyl chloride and is the most reactive of the three. Acyl chlorides, if you checked my first video, I said acyl chlorides are the most reactive organic compounds. Why? Because they're hydrolyzed by water at room temperature, right? Forming a completely dissociating HCl or a completely dissociating hydrogen halide species, okay? Acyl chlorides. They are hydrolyzed by water at room temperature, forming the completely dissociating HCl. Right, now let's move on to the next. The next one is number 2 is our chloroethane. Why? Because like the previous reactions before, we saw that this halogen can be substituted nucleophilically substituted by sodium hydroxide by boiling sodium hydroxide under reflux conditions to produce an ethanol, an alcohol, and a sodium halide, yet sodium chloride. The fact that it can be hydrolyzed makes it the second. The first one, however, here I actually wrote resist hydrolysis. But do we mean that it cannot be hydrolyzed? No, it can be hydrolyzed, but not under simple conditions, but under drastic conditions. So that's the explanation you give when you're giving those three molecules in an exam setup, to say one is the most reactive because it is an acyl chloride. It is hydrolyzed by water at room temperature. Number 2, this primary halogenoalkane is the second most reactive compound because it is hydrolyzed by boiling with sodium hydroxide in ethanol. Number 1, the halogenoarene now resists hydrolysis. It is not hydrolyzed under simple conditions but under drastic conditions. That's all there is to it. Now in closing, I need to talk about some of these compounds that involve these halogenoalkanes called chlorofluorocarbons, also known as CFCs, right? These are used where in anesthetics, right? They are also used in the manufacture of plastics and aerosol propellants. They are also used as gas in refrigerators and as coolant in air conditioners, right? CFCs have been banned in other countries because they are non-biodegradable. They pose a serious environmental threat. That's why hence the ban being effected in other countries. Okay, so guys, thank you so much for watching this video all the way to the end. If you found it helpful, I hope you found it helpful, and if you did, please support the channel by commenting, liking, and subscribing. And I'll see you all next time. Thank you.